Our next topic is the total energy of a particle in S.H.M. So to understand this very well, we have a spring mass system which is oscillating, right? And this is a very easy topic, please understand that, right? So this is a spring mass system where the mass is the one which is oscillating, right? And this dotted line represents the mean position. So this entire dotted line is the mean position. And we do know that the velocity is 0 at extreme positions. This is extreme position number 1. This is extreme position number 2. At time is equal to 0. This is 1/4 the oscillation. This is half the oscillation. This is 3/4 the oscillation. And this is 1 complete oscillation. So the time taken is capital T. So the velocities are 0 at the mean position, because velocity decreases becomes 0, increases becomes maximum, again decreases becomes 0, increases becomes maximum. So here and here velocities are 0, here velocities are maximum at mean position, this is also at mean position, so velocity maximum, and here also the velocity is maximum at mean position. So basically any particle which is performing oscillation will have two types of energies. Number one, kinetic energy due to its motion, and kinetic energy everybody knows that it is equal to half mv square. So wherever you have velocity 0, the kinetic energy is going to be 0. So the kinetic energy here and the kinetic energy here are going to be 0. Okay. By the way, the displacement over here y is plus a. It is a distance above the mean position, and here the displacement is minus a, because it is a distance below the mean position. So wherever the displacement is plus a, kinetic energy is 0, displacement is minus a, kinetic energy is 0. Now, what is the value of displacement here? y0, y0 and y0, because wherever the object is at mean position, the displacement is from the mean position. So the particle at mean position, displacement is 0. So here, and here, displacement is 0 as well as the velocities are 0. Sorry, velocities are maximum. So kinetic energy is maximum. Kinetic energy is maximum. And again over here, kinetic energy is maximum. How much is that value? We will see in the another paper. Okay. Now the value of potential energy is half ky square. This is due to the potential energy of the spring. You know that when the spring is in compressed or either in extended or pulled position, there is a potential energy associated with the spring. So when the spring is compressed or when it is extended beyond its mean position, it will have potential energy. So the potential energy here, it will have maximum value, and here also the potential energy will be in maximum value, because the spring compressed by maximum amount, spring extended by maximum amount. Now whenever the spring is at its own length, that means when the spring is at mean position, we don't consider the spring to be compressed or extended here, here and here. So basically the displacement becomes 0 here, here and here, so as the potential energy. And what is the value of that maximum potential energy? You might have guessed it right. Substitute the value of y over here and you will get the answer half k square. Okay, now let's move on. Just now we saw that the kinetic energy associated with the spring mass system which was oscillating was half mv square, and the potential energy was half ky square. We know these three equations: y, a sin omega t, velocity, first order derivative, that is a omega cos omega t, or you may also write it like this. Please refer to the previous lecture, right? Acceleration, again one time derivation of or one time differentiation of v with respect to time, you get this, or acceleration in terms of y is this. I am going to use these two over here, okay? So kinetic energy can be written as half m, instead of v I am going to write down this one, so that is omega under root of a square minus y square whole square. So basically when you open up the bracket, you get this as half m omega square a square minus y square. correct? This is the equation for the kinetic energy. For potential energy, you can stick to this one, that is half k y square itself. In most of the textbooks, what they do is they substitute this and this one and this one over here. So let me write that kinetic equation in terms of the sine and cosine functions. Half m omega square a square minus half m omega square y square. Now, before few minutes in the last lecture, I had discussed m omega square is k. So kinetic energy is half k a square minus half k y square. This is half k a square minus half k, instead of y I am going to use this, so half k a square sine square omega t. Okay, now this is the kinetic energy. Now the potential energy U is equal to half ky square, that can be written as half k a square sine square omega t. Okay, because simply I am substituting this here and here. Instead of this y and this y, I am substituting this to get these two equations in sine and cosine function. Not really necessary, but since it is given in the textbook, I prefer to do that. Okay, now to find out the total energy, which is very easy, I am going to add kinetic energy and the potential energy. So what am I going to get? The addition of these two. When I add, these two terms are going to get cancelled. So half k a square, k is constant, it is m omega square, a is constant. So the total energy is constant. This is only possible if we ignore the losses.